Prime factorization helps in finding the least common multiple. The first step is like the GCD. You do the prime factorization. You list your primes. In the least common multiple, you have to include every prime that's mentioned. Notice for the 8, the 2 is mentioned. The 14 has a 2 and a 7 as primes. And 16 has 2 as a prime. Now select every prime that is mentioned, 2 and 7. Now select the greatest power it appears with. The biggest power the 2 has is a 4, so you take the biggest power, 4. The 7, the biggest power is 1, so you take the 1. Now multiply those two. That gives you 112, which is the least common multiple for 8, 14, and 16. Here's a shortcut for the GCD. And the rule is like the formula. Notice on the left of the formula where you have the GCD A and B, it says it equals this. So instead of doing this, you could do it easier by first subtracting these two. In this case, 676 minus 221, the smaller from the bigger. That gives you a smaller number. And now you work with these two smaller numbers instead of the two original bigger numbers. Notice the only one that changed was the first one. The second was still 221. So now you do a factor tree for this, prime factorization, and that would be your GCD. The Euclidean algorithm, this is used to find a GCD of big numbers. Look at the big numbers, 10,764 and 2,300. The answer is 92, but let's see how we could find it using the Euclidean algorithm. So instead of using prime factorization, which would take very long because the numbers are very big, you use this method. So you start the division, you divide the bigger one by the smaller one. Then after you do the division, you move the remainder to the divisor position, and you move the divisor into the dividend position. Notice this one came up here, and this one came in here. Then you do the division, you get the remainder, it replaces the divisor, then the divisor replaces the dividend, and you continue until you get a remainder of 0. When you get a remainder of 0, then go to the previous division, the previous remainder, and that will be your greatest common divisor, which in this case is 92. So the GCD has a Euclidean method available, but the LCM doesn't. So if you're looking for an LCM of very big numbers, we would have to use the prime factorization, which could be a very, very long factor tree. So instead, we're going to use a formula where we could do the GCD instead, but find the LCM. And here's the connection between the two. This is the rule. This is the formula. So this is the connection. We would like to find the LCM, but going through the GCD. So isolate the LCM, which you're looking for, but instead of doing prime factorization, go to this side of the equation and work with this side, since you have the advantage of having a Euclidean algorithm for GCD for very big numbers. So notice A, B, these are the numbers that are here. Now you can work with the GCD side of the equation to find the LCM. So now that you've isolated the LCM, work with the GCD side, and here's an example. These are very big numbers, and we're supposed to be finding the LCM. So what we do is we plug it into this side of the equation. If we left it on this side of the equation, we have to do the prime factorization. But on this side, instead of using a prime factorization for GCD, you use the Euclidean algorithm. And you put the number here. The top two, which are the original numbers of the LCM, the A and B, you multiply them and then divide by what you get for the GCD of these two numbers. The ultimate answer on this side would be the same for this side, since this is an equation. This is the LCM for these two numbers.